Hello, my name is Philip Jones. I'm Professor of Physics at University College London. I'm here to talk to you as part of the Darwin College lecture series on the theme of isolation. This talk will be about isolation and trapping of particles using optical tweezers. I hope you enjoy it.
Good evening, ladies and gentlemen. Welcome once again to a Darwin College lecture, our fifth in this series. And as many of you will know, so far we have explored solitude and Persian poetry, the isolation of Australian asylum seekers, isolation and quantum security, and last week, of course, the geological isolation of Antarctica in the past. If you were foolish enough to miss any of those lectures, as you know, you can see them on the Darwin College YouTube channel, and of course, you can buy the book. I have to give it a plug as always. It's for sale up in the foyer, half price compared to what you would get it on Amazon, so I do encourage you to do it. It's a great read. So, today we turn from Antarctica and the vast land and ice mass of that continent on that scale to isolation of microscopic particles. And the fact that light can exert a force was known as long ago, I'm told, as the 17th century, with the observation that sunlight deflected the tail of a comet. For some reason, spacecraft can be diverted from their intended path by thousands of kilometers if the force of sunlight is not taken into account. And it was in the 19th century that the pressure from light was first observed to perturb a balance on Earth. But the realization that a laser could be used to amplify that effect led about half a century ago to the idea of optical tweezers. And that is, of course, the topic of our talk this evening. And the science has shown, and much of it has been led by our speaker today, just how exciting that story is. So our speaker is, of course, Professor Philip Jones, a Professor of Physics and Astronomy at University College London and leader of the Optical Tweezers group there. He studied natural sciences here at Cambridge and did a DPhil in atomic and laser physics at the University of Oxford before joining UCL. So, without further ado, please join me in welcoming Professor Philip Jones to give his lecture entitled, as you can see, Isolation of Particles Using Optical Tweezers. Philip.
Thank you very much, Master. Thank you for the kind introduction and for the invitation to come and speak to you this evening about something that is my research topic and fits nicely into this year's theme of the Darwin Lectures, the theme of isolation. So my research centers on optical tweezers, and we know what tweezers are. You know, we use a pair of tweezers to pick up and move small objects. And an optical tweezers is a device that does just that, but using light. So I'm going to tell the story here of just what an optical tweezers is, how they were invented, how our understanding of the fact that we can use something as seemingly insubstantial as light to actually exert force on matter and move it at will. The device itself was invented by this man. This is Arthur Ashkin, and he's going to feature several times in the talk. He made the first demonstration of optical tweezers back in 1985, and this was recognized with the award of a Nobel Prize, actually a half share of the Nobel Prize. The other half went to Gerard Moreau and Donna Strickland for church pulse amplification that year. And his citation was, for the optical tweezers, So the invention of the technique and their application to biological systems. I think one of the great powers of the technique is the wide uptake in disciplines beyond physics, in biology, in chemistry. I read a paper recently on the use of optical tweezers in forensic science. So the technique has become very widespread. And this, I think, is the power due to their ability to trap, to hold, manipulate, and indeed isolate microscopic and submicroscopic objects. As a quick demonstration, there will be more later. The objects you can see moving there are just 2 microns in diameter, 0.002 of a millimeter. They're colloidal polystyrene spheres, and they are being manipulated by optical tweezers. There's one that is being held in place, and the other is held and being made to perform this controlled motion around it. Okay? And there's no physical contact there. They're just being moved by light. So we have sort of remote manipulation without contact using light, which seems a little bit like science fiction. Right? So we know in science fiction we have things like tractor beams. Okay? So I guess most of the audience have seen Star Wars, and the Millennium Falcon is drawn into the Death Star by a tractor beam. That's why Obi-Wan Kenobi has to go off and destroy the machinery so they can escape again. But the idea of a tractor beam has been around for quite a while. I'm sure you're all familiar with the seminal work of E.E. Smith. I'm not getting a lot of recognition here, Master. I'm sorry. From the 1930s, the classic Space Hounds of IPC, if you haven't read it. This is where the idea of a tractor beam, that is, a beam that can continuously pull an object back towards its source, or, as it says there, the opposite, a pusher or presser beam, was first described in, I hesitate to say literature, but at least in the book. And this is in the 1930s. This is decades before the invention of the laser. Okay? Now, an optical tweezers isn't quite this. An optical tweezers is a device that can provide either a pull or a push to hold an object still at a defined point in space. Okay? So I'm going to spend the first part of the talk explaining just how our understanding of this has arisen. And we do need to go back quite a way. We need to go back about 400 years. We're going to take quite a long run up at this. So we're going to start not under the microscope, but in outer space. Okay? Bear with me. This is Hale-Bopp. Comet Hale-Bopp made a spectacular appearance, actually while I was a graduate student, so quite a long time ago now, 1997. And what we all know about comets is that they have a tail, and the tail extends behind the comet. But why do they have a tail? This is Kepler, Johannes Kepler. At the beginning of the 17th century, made observations on, in fact, the visitation of Halley's comet in 1607. Subsequently, wrote this book, I believe it means 3 little books about comets in Latin. Kepler's observation was that the tail of the comet always points away from the sun. And he described this as, well, this must be due to some action of light from the sun, and described it as though it were a cosmic breeze. And in fact, he wrote in a letter to Galileo, actually, that if one were to provide ships or sails adapted to the heavenly breezes, and there will be some who will brave even that void. Okay? Predicting, if you like, the use of what we now know as the solar sail. This is Light Sail 2, an artist's impression of Light Sail 2, that was launched into orbit just before the pandemic. In 2019, launched by the SpaceX company. So you can see that where Elon Musk goes, he is simply following Kepler 400 years after the fact. Let's leap forward around 100 years. At this point, much of the discussion around whether light can exert force on matter centers around the nature of light itself. Okay? Competing theories at the time. You have Descartes and Huygens' corpuscular theory of light, that light consists of small particles that are emitted from a source, as against the wave nature proposed by Young and Fresnel. This is Benjamin Franklin, who professed himself pretty much in the dark about light. And in his criticism of the corpuscular theory, as proposed by Huygens, was that these small particles that are being emitted from the sun must have some effect on dust and other small particles on Earth. And this was not observed. And in fact, the lack of any effect was taken by Thomas Young, because certainly the physicists amongst us will know of Thomas Young from his famous Young's double-slit experiment, that demonstrates the wave nature of light. Thomas Young took the lack of any observed effect of light on small dust particles as being supporting evidence for his wave theory. Things don't really get onto a firmer setting until we jump forward another 100 years, and here we have the Cambridge connection. Of course, this is James Clerk Maxwell. Came to Cambridge originally at Peterhouse, which is an excellent choice for college. Thank you. Although he later transferred to Trinity. Never mind. And he is famous, not most famous, for his laws of electromagnetism. This plaque here, which certainly the physicists will recognize, these 4 equations that summarize Maxwell's theories of electromagnetism. This is not the form that Maxwell set things down. This was done in subsequent work by people like Oliver Heaviside and John Poynting, who we'll come to later. This plaque is on a wall in Edinburgh, just close to a statue of Maxwell. And Maxwell observed that pulses of electromagnetic radiation traveled at the same speed as light, and therefore he deduced that light was indeed electromagnetic radiation, carrying energy, and carrying energy in a wave must therefore exert some pressure. And he calculated that the energy falling on the Earth's surface would be equivalent to, I apologize for imperial units, 83.4 foot-pounds per second per square foot, which exerts a pressure of 10 to the minus 7 pounds per square foot. Converted to perhaps more familiar SI units, on a hot sunny day at the equator, the pressure from sunlight on your head is around about 5 micropascals. Okay. On a slightly dull February afternoon in Cambridge, a little bit less. Okay. So it's probably not surprising you don't notice that. Atmospheric pressure is, 100 kilopascals? 11 orders of magnitude greater. If you care to calculate the force, you take a sensible estimate of the area of the top of your head, and that force is about 1 million times less than the weight of a feather. Fairly insubstantial. Now, after Maxwell's death, his work was continued by one of his former students. This is John Henry Poynting, studied under Maxwell, also under Thomson in Manchester, later became the first professor of physics in Birmingham. And he continued Maxwell's work on electromagnetism, and he was greatly interested in radiation pressure, okay, what the pressure exerted by light. He too realized that the pressure was indeed extremely small. He expressed it as less than 1/2000th of a grain on the square inch, something I'm not sure I could convert to SI units. And these days, certainly as academics, we are under great pressure to publish, and publish in the most high-status journals. We want to publish in Nature, in Science, Physical Review, and so on. John Henry Poynting published his first works on radiation pressure, not in any of these, but in a magazine, The Enquirer, which is a periodical of the Unitarian Church, of which he was a member. So he wanted his ideas about radiation pressure to receive a wide audience, just as we have here tonight. Now, Poynting knew that the forces exerted by light were indeed very small. He became president of the British Physical Society, and in his inaugural address, he stated that a very short experience in attempting to measure these forces, that is, the forces that light exerts on matter, okay, sufficient to make one realize their extreme minuteness, which appears to put them beyond consideration in terrestrial affairs. So it seems as though radiation pressure, the force exerted by light, is negligible in everyday life and potentially of no use. But he did go on to say, the effect of radiation pressure on terrestrial dust is worthy of consideration, for it may be quite appreciable when particles are small. It certainly is. Of course, it's all very well having a theory, but we need experiments to back it up. By the beginning of the 20th century, there was the start of some experimental evidence to try and measure the mechanical effect of light, radiation pressure. One of the great challenges is, of course, distinguishing the effects of light from the effects of heat, so photophoretic and radiometric forces. Great advances made by Lebedev, Ernest Nichols, Gordon Hull, working in America. Nichols and Hull, in particular, measured the magnitude of radiation pressure and obtained a result that agreed with Maxwell's prediction to better than 1%, which sounds too good to be true. As it later turned out to be, it was perhaps too good to be true. They made a number of errors, taking a wrong value for a heat capacity, taking logs to base 10 instead of base E, and so on. Several of these happened to cancel out, and they ended up with a very good result, which presumably they didn't question because it was so close to what they expected. The true value recalculated. I should point out, this part of the talk is all men, mainly men with moustaches. The error was pointed out by a scientist called Mary Bell, a woman. She pointed out their error. Their results were still pretty good, actually. Agreed with Maxwell to within around about 10%. There's a great account of this story in a paper entitled A Selected History of Confirmation Bias. I think it's a great title for a paper. So we have the idea that light can exert a force. We have the beginnings of measurements of the force that light can exert, hampered somewhat by the fact that these forces are so small. Experimentalists are using thermal light sources. It's not really until the invention of the laser that things can take off. Okay? So now we enter the story with Arthur Ashkin, the man we met earlier, who invented optical tweezers. He was born in Brooklyn, New York, the son of Ukrainian Jewish parents. Studied physics at Columbia, following his older brother Julius, at Cornell. His time was interrupted by the war. He studied nuclear physics. After graduating with his PhD from Cornell, he went to work for the Bell Telephone Laboratories in New Jersey. He was very interested in the mechanical effects of not just light, but electromagnetic radiation, including microwaves and so on. And the telephone lab supported this work, as they did much other research which, at first sight, doesn't seem to be closely aligned to the interests of a telephone company. We were discussing Nobel Prizes earlier with the master. The Bell Labs actually laid claim to 9 Nobel Prizes, 8 in physics and 1 in chemistry. Some very significant advances. So Penzias and Wilson was the observation of the cosmic microwave background. Clinton Davison for the wave nature of matter. Steve Chu, who will come up in our story again for laser cooling and so on. So remarkable success in the order of 9 Nobel Prizes, and perhaps slightly curiously, an Oscar. A technical Oscar in 1937. There are 2 individuals who have won both a Nobel Prize and an Oscar. Perhaps over dinner someone can tell me just who they are. It's worth asking why Bell Labs was so successful. This is Mervyn Kelly, who is the director of research, and he said the non-scientific duties of management should be minimized for all levels of the research supervision. There should be the very minimum of diversion of the attention of the research leadership and the individual researchers from their scientific programs. So let the scientists do the science and not the management. I will let those words settle over the audience. Yeah. It also helped that they were very generously funded, to the tune of $2 billion in 1982, before AT&T fell foul of American antitrust regulations and the labs were broken up. But into this very productive research environment came Arthur Ashkin, interested in radiation pressure, the mechanical force of light, work that was supported. The phone company took a very long-term view. They said, don't worry if there's no immediate application. We'll catch up. We'll get there. So let's have a look at Ashkin's ideas, how he reasoned that radiation pressure should be something that's measurable. Okay. A quote from him. Suppose you have a laser with a power of 1 watt. We focus that to a small spot, about 1 micron diameter. If that hits a particle of a similar diameter, at 1 micron, and just imagine that all that light is reflected back off the particle. Okay. And then we ascribe a density for convenience, let's say 1 gram per cubic centimeter. It's about the density of water. It's not unreasonable. You can estimate an acceleration that reflecting particle should receive. And that acceleration turns out to be 1,000,000 times the acceleration experienced by a body in free fall due to the Earth's gravity. Okay. As Ashkin said, this is quite large. Indeed it is. And should give readily observable effects. So the key here is that we have the laser. Okay. We have a bright, intense source of light. We're not reliant on sunlight or on thermal sources. Just have a look now at exactly what Ashkin meant. Ashkin's reasoning behind this is simply something that we learn as physicists. One of the very first things we learn when we start to study physics is conservation of momentum. Maxwell's told us that light carries momentum. So imagine we have a wave, it has a momentum, call it P here, which is actually Planck's constant h divided by the wavelength. And it's reflected from this small mirror, and so it bounces off the mirror and goes back the opposite way. Carry on. The direction of its momentum has been changed. Now, what happens there can be solved by application of conservation of momentum. Something we do when we start doing physics. We have many, many internal problems on solving collisions of billiard balls or projectiles colliding in the air, and what happens. As in the poem, gain a body, meet a body, flying through the air. Gain a body, hit a body. Will it fly, and where? I can't judge the quality of the poetry, but the poet is our friend James Clerk Maxwell. So I think he knows what he's talking about. We know where the mirror will fly by considering conservation of momentum. All the momentum in the first picture is directed towards the right. In the second picture, the momentum of the wave has been reversed, pointing towards the left. Momentum must be conserved. Okay? So the difference must be taken up by the mirror, and it must move to the right, with a momentum that's twice the original momentum of the wave. So will it fly, and where? Yes, it will, and it will fly along the direction of propagation of our laser. This is radiation pressure in action. So Ashkin reasoned that radiation pressure should be large enough to be observed, and like a good physicist, I tried a simple experiment. Always best. And it's a very successful experiment. This experiment, which the intention was only to show this forward motion that we just saw with our little toy example of light hitting a mirror, also showed, what was not suspected, the existence of a force not just along the direction that the laser is traveling, but also perpendicular, the transverse force, and applications including guiding particles, trapping, sorting, and so on. This is Ashkin's simple experiment in his own drawings in an article he wrote in Scientific American, 1972, shortly after the first experiments. He had a tank, a cell, that contained water, and in that water were suspended small, transparent spheres. And he shone a laser beam through them, expecting to see that particles would be pushed along the direction of the laser beam. Now, doing this in water and with transparent particles helps to reduce the effects of heat and confounding thermometric, radiometric forces. Okay? So he could be fairly sure that what he saw would be due to light and light pressure. And what he saw was that not only did the particles move along the direction of the beam, but they were pulled in from the side. Okay? This here is supposed to be a sort of an end-on view, and particles would freely wander around, actually doing Brownian motion, and when the beam was switched on, they'd be pulled across the profile of the laser beam and then projected along it to gather against the wall of the cell. Why is this? Well, Ashkin's explanation, again, actually relies on something that we learned very early on in our physics careers. It relies on the laws of reflection and refraction, coupled with conservation of momentum. Let's use Ashkin's drawings again. This is a drawing from his paper where he first demonstrated this. This is one of the spherical particles he has. This illustrates the laser beam. The form of a laser beam is that the intensity is highest on the axis and it drops away towards the wings. Ashkin said, consider a ray, a little portion of that beam. Consider this one labeled A. It strikes our small particle. Now, this might be a particle of glass suspended in water. It has a high refractive index, so it works like a lens. It bends, it refracts the ray of light as it crosses. So our ray A here crosses the particle, ends up its path being bent, coming out at a different direction, which means that the direction of its momentum has changed. There must have been a transfer of momentum from our object, our particle, to the ray. And therefore, Newton tells us there must be an equal and opposite transfer of momentum from the ray onto the particle, as indicated by the arrow here, the force Fa, the force exerted by that ray A on the particle. Now, unfortunately, there are also rays, such as ray B, striking like the lower hemisphere of this particle, which are bent in the other way. Now, they will exert a force in the direction shown by the arrow FB. So two competing forces, however, ray A is closer to the axis of the beam. It has a higher intensity. So the force exerted by A is much greater. Okay? So the net force, the overall force, pulls the particle. And it pulls the particle because there is a gradient of intensity. Okay? Because the beam is brighter in this part than this part. It pulls it across the profile of the beam into the brightest part. Okay? Because this force, arising from refraction, depends on the fact that there is a gradient of intensity. Ashkin called it a gradient force. So that describes the motion of the particles across the beam. We said, remember, they're also projected along the beam. This is the so-called scattering force. Whenever we have two media with slightly different refractive indices, there will be a small reflection. Not 100% reflection, like looking in a mirror, but a small reflection, more like looking in a window, when you see a very weak reflection of yourself. So there will be a small reflection from these rays A and B. That reflection projects a portion of the ray backwards and therefore pushes the particle forwards. So the small reflection gives rise to this pushing along the beam that Ashkin called the scattering force. So his explanation of his observations, real observations of radiation pressure, we've broken down in terms of reflection and refraction. The particles are pulled into the beam, they're projected along. We thought, well, if you just apply another beam going in the opposite direction, we can balance those scattering forces and hold particles in the middle, which indeed he did. This is his drawing of the experiment. This is Ashkin's lab notebook. I always try to impress on my students the importance of keeping a good and accurate notebook. And this is Ashkin's account of the proposed experiment. I do, like he said, I have discussed this with E.P. Ippen and P.A. Wolf, who both became professors at MIT later on. P.A. Wolf, before he left on vacation. Lesson there is don't go on holiday, you might miss something from the lab. Right. In that experiment, Ashkin balanced the pushing effect of a laser beam with the pushing effect from another beam. Another way you could do this is send the beam upwards instead and balance the pushing effect of the laser beam going upwards with the weight of the particle acting down. Ashkin called this optical levitation. Okay, this is his drawing of the apparatus. This is the levitating beam, comes in its focus, reflected upwards, it pushes this particle up. This second beam here is there so the particle will scatter light so that you can see it. And this is a photograph of his experiment. And you can see the path of the laser beam here and this little bright twinkling dot there. A levitated particle. Okay. So these experiments are taking place really in the sort of the 1970s, the early 70s. It was later on that Ashkin then developed what we call the optical tweezers. Okay. So remember what I said we need for optical tweezers is that a particle is held at a point in space. Okay. It's not pushed or pulled. And it's held there not by force arising from reflection, the scattering force, but only by forces arising from refraction, the gradient force. This experiment first done in 1985. And the key, Ashkin realized the way to do this, to create a gradient force that will hold the particle along the axis, is to create a gradient of intensity along the axis. And you do that by focusing the beam. You think as you focus a beam, it becomes narrower, it diverges again. As you go along the axis, it's getting brighter and then fainter again. Work was published in the journal Optics Letters. I believe this still, it's all about citations when you're publishing papers, but I believe this still remains the most highly cited paper in the journal of all time. It's also worth noticing, received 1985, accepted in 1986. Ashkin was 63 at the time. And this is the work that he later won the Nobel Prize for. Okay? So the message I take from that is that there's still hope. Just. So Ashkin's great realization there, the way to trap the particle is to create this intensity gradient by focusing. So what we can see, we're familiar with these ray diagrams. Now, if we focus our Gaussian laser beam, there's intensity. If we look at these rays that are coming from the edge of the beam, this ray comes here, my particle is below the focus here. This ray gets bent downwards. So you can see the direction of transfer of momentum to the ray is down, which means that it must be pulling the particle back up towards the focus. Of course, there's this pesky effect where you get a small reflection using the scattering force. Okay, this small portion of the ray is bent that way, so there's a force on that portion of the ray acting upwards, so the scattering force is acting downwards. Okay? So we've got competition between the gradient force from refraction pulling back towards the focus, the scattering force from reflection pushing away downstream of the laser beam. Ashkin realized you can make the gradient force win out as long as you focus very strongly. And the key to doing that is to use a microscope objective lens, which is great because it then serves the dual purpose is that you can actually see the microscopic particles you're trapping. So the particle is pulled towards the focus. It actually sits not exactly at the focus, because of this small scattering force that pushes it a little bit. And it turns out that when the particle moves a small distance away from the focus, it feels a force that pulls it back. And that force is proportional to the distance it's moved away from the focus. So the physicist would write that down, that the force is minus, the opposite direction, some constant, the constant of proportionality, multiplied by x, the displacement. And this is something else we learned way back at the beginning of our physics careers. This is simply Hooke's law for a mass on a spring. And this is Robert Hooke. You probably wouldn't recognize this. He wrote this in Latin, latentio sic vis. So, if you really want to know the forces that are acting on your microscopic particle, what you do is you take your bundle of rays that form your beam, propagate them, focus them, an objective, look at their intersection with the particle, refract them, propagate them across the particle, refract and refract, sum up all the momentum changes, and that's your force for the particle at that position. Then you move the particle, do it all again. Move the particle, do it all again. This is what you have to do. It can be quite a lengthy calculation, depending on various complicating factors, particularly the shape of your particle. For a sphere, it's relatively quick. These diagrams here are sort of force maps, if you like. This one top right, this is in the transverse plane. All those arrows point inwards to the axis. Right? They show that your force is directed inwards and hold the particle on axis. This one here, all those arrows point, it turns out not quite the origin there, but it's actually slightly along the direction of propagation due to the small effect of pushing radiation pressure. Okay. So Ashkin sprang into action. You remember his Nobel citation was for the invention of optical tweezers and their application to biological systems. Right. Here we are, 1987. 1987, 2 papers, one in Science, one in Nature. I think if I got Science and Nature in the same year, I would retire, full stop. Ashkin was 65, the age at which, well, I'm probably not going to be able to get to retire, but you get the picture. He was still active doing research, trapping. The first one, viruses and bacteria. So tobacco mosaic virus, first of all. This is his setup. This graph here, these little steps. This is measured light that's being scattered by what's in the optical tweezers. And little steps correspond to individual virus particles entering the trap. Also trapped bacteria, E. coli bacteria. There are some perhaps apocryphal stories about the origin of this experiment. Some say it's a sample that became contaminated overnight. Others say the sample was cultured from his colleague Joe Zidich's ham sandwich. Nevertheless, he trapped E. coli bacteria. Furthermore, in later experiments, same year in Nature, he could trap bacteria such that they remained viable. They could still swim, they could still reproduce. The key there was being very careful about the laser he used, selecting the right wavelength. It turns out that infrared light is absorbed relatively weakly, and so biological material, bacteria, cells, and indeed subcellular structures, as he showed in this paper, could be manipulated in the optical tweezers. Now, I was talking with David earlier about optical tweezers. Where can you get an optical tweezers? Because this all sounds great. You can buy them. You can bolt one onto a microscope if you want. You can buy a kit form, or you can build your own. This little animation, grateful to Pepe in particular for putting this together. Most optical experiments take place on a large vibration-insulated table. Okay. Now, an optical tweezers, it's basically a microscope, so you can build up your own microscope here. I put on a stage on, that's where your sample is going to sit. You need something that holds the objective lens there. Microscope, you need a stage, so you can move your sample around and see what's going on. Very nice to have one of these piezoelectric stages because they can move with nanometer precision. They're expensive, though. Build the microscope up. Here we have the illumination detection plane, putting your apparatus for holding the condenser lens, putting your objective, crucial for seeing what you're trapping and doing the trapping. Make a sample, simply preparing something to put on the slide in a holder on top of the microscope. Putting the condenser lens, this is what focuses the illumination light onto the sample. Of course, we need to see what's going on, so we put a camera on it. You shouldn't look into an optical tweezer with your eyes. There's a laser on. It will cause damage. Trace out the beam path onto the camera. That's a microscope. And what you can see in the microscope, things like that, these particles, which you can then do microscopy on and track their position. To make an optical tweezers, you need to add a laser. There's some optics there. These are just being used to control the intensity of the laser. We need to combine that in the same optical path that we're viewing along. So we have a dichroic mirror. That's something that will reflect the laser light but allow the illumination light through. Beam goes there and it shoots straight up the microscope to be focused by that objective lens and form our optical trap, our optical tweezers. And there we have a trapped particle. That one's being held there. You see the stage is being moved around. The particle stays still in the middle of the field of view. You can see some of the little shadows there, other particles doing Brownian motion in the background. There's our optical tweezers. Just to summarize there in the movie, on a still there. This is a photo of the setup in sketch form and here a demonstration of optical trapping. Which all sounds great. But some of you may be thinking, why? Why do this? Why do you want to isolate particles? Well, as a physicist, we want to isolate particles to remove external influences. We want to know what we're doing to what we're experimenting on. We want to control the environment, okay? Remove external influences, external forces, and apply a force or some other interrogation that we know what we're doing. So here is a particle, you saw there, being isolated from others in the sample. It was held in the optical tweezers, and you saw the others fading away from view as we move it vertically. That's about 4 microns in diameter, that one. Difference about this one, this is a bubble. It's a microscopic bubble. And so because it has a low refractive index, because it's air surrounded by water, everything I said to you before, reverse it. the bubble is not trapped by optical tweezers, it's pushed away. So we get around that by scanning the laser very quickly in a circle around it, sort of cage it in the dark hole in the center. Okay. Not just bubbles you can trap. This diagram here is intended to represent the whole zoology, if you like, of stuff that has been trapped in optical tweezers, ranging from the micron size, the cellular level, down to sort of nanomaterials, viruses, that's what Ashkin did, even down to single atoms. Slight twist and complication is that as you get very small, the trapping force tends to scale with the volume of the particle. So if your size, transverse size, drops by a factor of 10, your force tends to drop by a factor of 1,000. So the forces do get very weak in this regime. However, with species such as atoms, you can exploit things like atomic resonances to amplify basically the polarizability, and they do become trappable. So a great range of size. We're going here from 0.1 nanometers up to 10 microns. And it's the same physics all the way through, really. The interaction of laser light with trap particles. But we should ask, perhaps, are these particles really isolated? Well, we certainly isolate them from other particles of the same type. And we saw that video with the bubbles. The bubbles are isolated from other bubbles. But it's still suspended in a liquid, suspended in water. And so all the time, it's undergoing bombardment from the molecules of the suspending fluid. And this is Brownian motion. So here's Robert Brown. He made these observations a long time ago with pollen grains, that the microscopic pollen grains were never still, always jiggling. So while particles might be isolated from other particles, they're not necessarily isolated from their environment. This is no bad thing, because actually that random motion of the particles that are held in the optical tweezers gives us a way of determining the relationship between the force you apply and the resulting movement of the particle. It gives us the stiffness of that optical spring. Okay? It's a slide for the physicists, really. This is basically measuring the displacement of a particle as it does jiggling Brownian motion in a trap. Okay? I used to do this, so I'd say, this is doing random motion, and then one of my colleagues probably said, it's not random, it's an Einstein-Ornstein-Uhlenbeck process. He's absolutely right, it is. It's a random motion that's dominated by steps back towards one particular value. Here is random motion around about zero, because the particle does its random motion around equilibrium. And basically, there's a number of ways of processing the data. Because we understand Brownian motion, we understand the statistical properties of such a distribution, that we can process the data, obtain these curves. These are just different ways of processing. Fit the curves, and this gives us the stiffness of the optical spring, the relationship between force and displacement. Which means that if we have a particle that's doing Brownian motion there, and these arrows represent the optical force field that's confining it at equilibrium, we apply an external uniform force field acting from left to right there. That will push the particle left to right. Here it is doing random Brownian motion around its new equilibrium. It's just displaced by some small amount called delta x. And the problem of measuring the force that's exerted on it comes down to simply measuring that displacement, because we know the relationship between force and displacement. An example here. Here we have a microscopic bead under the red dot there, and it's stuck onto a cell, a stem cell. And that cell is then pulled away, and there's a small, wispy, it's called a membrane tether connecting the cell to the particle. Now, as you see, the particle is pulled out of the trap until it's completely lost. Pulled out of the trap a small distance. If we measure that distance, then we know the optical force that's pulling it one way, and we know the force in the membrane tether that's pulling it the other way. Those forces must be equal when it's at equilibrium. And therefore, we can actually measure the membrane tension of the cell simply by measuring the displacement of the particle. I should thank, for this video, Henry de Belli. Henry was a PhD student with Eva Paluch in UCL, then in Cambridge. And I think it's important. I talked about Ashkin being probably near retirement age when he did his work. Most of the work the experimental work that we do in labs is not done by people near retirement. It's done by the PhD students, okay? The younger students, the students I met at tea with the master earlier. So I think it's important to credit them. So Henry did this, some fantastic work measuring the membrane tension in stem cells and how that undergoes a sudden transition and change in membrane tension that allows the stem cell to exit its pluripotent state and take on its final form. So we now know all about optical tweezers, where optical forces come from. What can an optical tweezers do? I wanted to tell you about some experiments. I'm kind of spoiled for choice because there's so much that an optical tweezers can do. This image is taken from a recent, it's called the Roadmap for Optical Tweezers. Many authors have contributed ideas about future directions for optical tweezers research in various fields, biophysics, combination with spectroscopy, even optical forces in space. But I thought, perhaps for the Darwin lectures, I'm going to look back, not 1 year, but 2 years. I know we have many regular attendees at the lectures here who may well remember that 2 years ago the theme was blood. Okay, so optical tweezers as applied to blood. We know that our blood contains erythrocytes, red blood cells, and we know that they have, this already, this classic so-called biconcave disc form. They're about 8 microns across. An adult human has tens of trillions of these circulating in your body. It takes about a minute to go around. Okay. Can we trap red blood cells? So we know about ray tracing. We've learned that. So to learn whether we can trap a red blood cell, we trace a bundle of rays. We find that intersections with the cell. We reflect and refract them. We propagate them across the cell. We reflect and refract. We sum up all the momentum transfers, and this gives us our force. Right? It's quite complicated for a cell. Even that change in shape from a sphere to a biconcave disc does make this calculation rather more complicated. So I definitely have to thank here Ricardo Sognatto, who's a PhD student with me, graduated last year. But it turns out if we just start these videos here, this is how we calculate the force. We locate the cell, we do our ray trace, we calculate the force, we move it, we ray trace, calculate the force again and again and again. And eventually we can produce force against position curves. And what we're looking for, if something is trapped, is that the force against position curve basically slopes downward left to right. Okay? Which means as the particle changes in position, the force increases proportional to that change in the opposite sense. And what we see here is transverse displacement against the force. Actually, we see 2 locations. And this is because of the shape of the cell. Right? It's not a sphere. It's got a wider part around the edge. So these 2 trapping locations correspond to the beam, gripping that thicker part around the edge of the cell. Similarly up the axial direction. Okay? So it should be possible to trap a cell. But the other added complication is that it's not spherical. The cell experiences not only a force, but a torque. Okay? The light will also cause it to rotate. How will it rotate? And what's the torque look like? It turns out, so instead of a force displacement curve, this is a torque angle curve. We can find, again, positions of stability. And these turn out to be basically corresponding to this orientation here. So if our beams are propagating up and down Z, the cell we pull to the beam and also tend to flip to line up along them. As I said, these are very involved and complicated and quite lengthy calculations. Ricardo was at a conference during his PhD, and he met another PhD student, David. He happened to be a student of a long-time friend and collaborator of mine. And David had been working on neural networks. Everyone wants to do machine learning these days. And so Ricardo and David got together and said, well, can we apply neural networks methods to these force calculations? Can we train a neural net to calculate the optical forces? Long story short, yes. There's the details of their neural net there. Inputs are basically the position orientation of the cell. Outputs are the forces and torques. Okay? And the results of the neural net are excellent agreement of actually doing the ray trace from scratch. With the advantage, it's 100 times faster. This allows us to do live Brownian motion simulations of the cell. So if you want to trap cells, now you're convinced that you can trap them. This is a sketch of our optical tweezer situation. We want to make two beams. Okay. So essentially we divide and recombine the laser, and we shine it on the microscope, and these two beams will then grip the cell at these wide parts here, diametrically opposite points. Okay. The cell flips up, we're looking at it sort of side on. One of the beams has these steering mirrors in, so we can control the position of it remotely with the computer. Okay. So we position the two laser beams over the cell, as shown in the cartoon. This is an image under the microscope. Don't know how clear the cell shows up, quite poor contrast. Then as we lift it away from the surface, the cell flips and rotates, so we're looking at it edge on. Why? These experiments stemmed from an email out of the blue from Rupesh Agrawal, who's an ophthalmologist who's actually he's from Singapore, over in UCL, doing a PhD in mechanical engineering, because he's interested in the viscous properties of blood and how they affect eye conditions. Diabetic retinopathy, a condition that many people with diabetes suffer from. Okay. Around about 80% of all patients who have diabetes for more than 10 years end up suffering with diabetic retinopathy. The symptoms are ultimately a loss in eyesight, which arises from small blockages in the microvasculature of the eye. They become blocked, they burst, they leak into the eye, new blood vessels start to form, they're abnormal, they encroach on the retina. Ultimate cause is blindness. The leading cause of new cases of blindness in the United States. To give you an idea of how significant this problem is, these are figures for the growth in patients with diabetes. Okay. In 1985, up to a projection of 2030, this is millions of patients up the axis here, projected to be around 550 million patients with diabetes worldwide by 2030. To give you a sense of scale, I checked this morning, and there were a reported 670 million coronavirus cases over the course of the pandemic. So a problem of similar magnitude to coronavirus. So we did the experiments using Rupesh's connections at the Moorfield Eye Hospital, collected blood from patients, patients with diabetic retinopathy, patients without, and a control group. Did all the routine blood tests that they have, and then tried to persuade them to allow us to do some experiments on their blood. That's actually the hardest part, is getting people to allow you to experiment on their blood. Once they agreed, then hopped on the tube, brought a small sample of blood 3 stops down the Northern Line to UCL, where we did this. We stretched them. So that's our cell, held in the optical tweezers, and all we're doing is slowly increasing the separation of the two laser beams. And as you can see, that pulls, stretches the cell until we let it go, and it relaxes back to its equilibrium length. By doing this, we can get some measure of the deformability, how easy it is to stretch the cells. Do this by recording videos. We can detect the outline of the cell and trace it. And you can see here, this is the extension of the cell as we pull. The red line shows the displacement of the laser spot. As we move the laser, it stretches the cell. Okay. Cut a long story short, we take blood cells from many patients. We experiment on many cells. Fortunate to have 2 extremely patient PhD students, Chris Richards and Tom Smart, to do this. And we find that patients who have diabetic retinopathy do indeed have cells that are less deformable when subject to this stretching. Little caveat there. Less deformable than healthy patients. Okay. Why is this important? Well, you remember I said that a red blood cell is about 8 microns across. The smallest microvasculature in the eye is only about 5 microns. Blood cells need to be able to fold and distort to pass through. Okay. Bearing in mind you've got 20 trillion blood cells, okay, going around the body once a minute, and they live there for 120 days. If you've got cells that can't fold, that can't squeeze through the microvasculature, there's a good chance they'll find it and get stuck. So our inference is that perhaps the conditions associated with diabetic retinopathy are in some way related to the mechanical properties. A little bit of supplementary data. We also investigated cells from a condition called birdshot chorioretinopathy. No, I hadn't heard of it before either. I think the keyword there, it's an uncommon bilateral inflammation. It's thought to be hereditary. The importance of studying this is that patients with birdshot tend not to exhibit the same thrombosis in the microvasculature as patients with diabetic retinopathy. So in testing cells from these patients, indeed, we found no significant change in the mechanical properties of the cell, perhaps suggestive that our supposition is correct. Okay? The condition, diabetic retinopathy, influences the mechanical properties of the cell. We don't know how, and that ultimately leads to the sort of symptoms we observe. Have some small amount of data from patients with a condition called Behçet's disease, but it's really very uncommon, so we can't deduce anything from it yet. Other conditions we might like to study, so Ricardo did some simulations here. Sickle cell disease is perhaps an obvious target. Red blood cells don't have that nice biconcave discoid form. They become distorted into this very characteristic sickled shape. Now, I said nice biconcave form. Finding the forces on a healthy red blood cell was quite tricky. Even with the symmetry you have in a biconcave disc, in this sickled shape, it turned out to be really quite complicated. Ricardo was very ingenious in this. And he made use of the techniques that are used in CGI and computer animation. So when you see these very realistic computer animations that have the lighting is apparently real, use the same techniques you have there to calculate your ray paths and intersections, to calculate the ray intersections with the cell, and therefore the forces. The sickle cell, it turns out, can be trapped, but the behavior is very odd. It has a number of stable orientations. So I'm coming to the end of my time and my talk, just to highlight a few other experiments that we do in the lab. Let's stop all these playing. There we are. The top left, this is a video. It's rather like Ashkin's first experiment, trapping particles with counterpropagating beams using optical fibers. This thing here, this is an oil droplet. It's an oil droplet that's incredibly soft. So by controlling the temperature and the salinity of the surroundings, you can make the interfacial tension of that oil drop reduce, and reduces by a factor of 1 million, to the extent that we can stretch and distort it with optical tweezers, which is great. Top right, this is a realization of an optical pendulum. The physicist might be familiar with this so-called Kapitza pendulum. Pendulum on a rigid rod, like in a grandfather clock, it oscillates downwards. If you oscillate the point at which it pivots, it has a stable orientation upside down. We tried to reproduce that with an optical tweezers by making an optical pendulum, and it turns out that because it's suspended in water, it's overdamped, it'll never fully invert. It never goes halfway. Supposed to be talking about isolation, but these are some experiments that I do like. This is actually multiple particles self-ordering. Okay? These particles spontaneously self-order here into an almost perfect lattice, just due to their interaction with laser light. So it's called optical binding. And it's not only light you can use. You can use sound to manipulate particles as well. Thanks to Anna Jorgensen for this. This is acoustic focusing. A lot of particles flowing down the microchannel. We put on an acoustic wave, transverse the channel, focus them into the center. This is from Chris Fury, a former PhD student of mine. This shows, again, acoustic trapping. These are our microbubbles again. We like microbubbles. Being trapped in the node of an acoustic standing wave. Just above that is a video, again, David of the neural network sent me this. This is an acoustic levitator. Do you remember Ashkin's levitator with a laser beam propagating upwards? Here you've got an acoustic field formed by this array of transducers, and you've got little particles bouncing up and down in the acoustic field there. Doesn't look like David's hand, actually. Looks like Maria Grazia. On the right, this is a much smaller particle. So what I think David is interested in is analyzing space dust from meteors. And this is a substitute for meteor dust being levitated in an acoustic trap. So, manipulation, isolation of particles with light and with sound. So I've come to the end of my time, really. Many people to thank. So, as I said, Ashkin was probably retirement age when he invented optical tweezers. But in the lab, this work is really done by the younger people, the PhD students, former PhD students. I've mentioned some of the names: Chris, Tom, another Chris, Nick, Ricardo, Anna, Alessandra, and David, who spent some time in the lab as visiting students. The current group, these guys all started in September, actually. They're still quite new with me. It's Bingxin, Shidem, Shi, and Nina. Sandrine's not shown there. She's away in Portugal this week as a training program. It's part of her training network. That really is the end of my time. But I'm going to give the last word to who else but Arthur Ashkin. He was asked for where might optical tweezers go in the future, in an interview about 1999. Here he is. This is Arthur Ashkin in his home laboratory. My wife's at the back. At the words home laboratory, she was there. He's asked to make predictions about the future, and he quotes the legendary American baseball coach, Yogi Berra. It's hard making predictions, about, especially about the future. But nevertheless, he did, 20 years ago, predictions about the way optical tweezers can be used for the forces between colloidal particles, crystallization, droplets. Applications to biology will continue to grow explosively. Well, that's certainly right. Absolutely true. Studying mechanoenzymes manipulating structures within cells. But the last sentence, I think, says it all. Finally, I predict the future will bring other new things which you and I haven't even thought of yet. And with that, I'll finish. Thank you very much.
Thank you very much indeed, Philip, for a fascinating and stimulating talk, so beautifully delivered. Just briefly to reflect on this, I'm pleased to invite Sandra Petrus-Rura, who is a research fellow at Darwin and in the Department of Surgery at the University of Cambridge, a biologist, to reflect on Philip's talk. Over to you, Sandra.
So thank you, Master, and thank you, Professor Jones, for such fascinating lecture. It is a privilege for me to now reflect on some of the key messages that this talk leaves us with. Professor Jones guided us through the origins, history, methodology, and applications of this instrument, which is able to use its light touch to trap a single microscopic or submicroscopic particle, and it is able to isolate it from its surroundings in a contact-free and damage-free manner. I must admit that my initial naive thought when I first heard about optical tweezers was, but what do we need? Why do we need this for? The lecture made clear that their impact is far beyond a laser beam, extending it to the field of biology, nanotechnology, and non-equilibrium physics. Professor Jones mentioned some specific examples on such applications, including the ones in the written paper, that I would like to re-emphasize. Optical tweezers enable detailed understanding on mechanical and torsional properties of the DNA. They clarify the correlation between cell stiffness and disease phenotypes. They allow the generation of fluorescent proteins and biomimetic bioreactors. They are capable of trapping nanomaterials, including graphene, or patterning a substrate in a controlled manner. And they enable the study of complex phenomena, such as dynamic mode locking and dynamical stabilization. Despite the challenges linked to a technology that gained most insights from particles freed from their complex environments, optical tweezers are in clear evolution and branching towards the use of not only light beams, but also magnets, line patterns, optical binding, or acoustic fields as alternative capturing forms. The combination of complementary cutting-edge and high-throughput technology will bring this optical trapping and manipulation tool to another level, and will definitely lead to new applications in a wide range of fields, many of them still unknown to us. I would like to conclude this reflection with two additional thoughts. Understanding things at the level of minuteness and detail is what has made us humans influential creatures, bigger thinkers, and outstanding at interacting with our surroundings. Also, it is the freedom given to scientists, freedom such as the one Arthur Ashkin had, that allows exploring the mysteries of the detail and the mysteries of the unknown, and which undoubtedly is our most powerful weapon to make an impact in the future world. So thank you once again, Professor Jones, for shedding light to a microscopic field that today brought us into a captivating macroscopic discussion. Thank you.
Thank you very much, Sandra. And once again, if you want to know more, it's in a book at the back. So don't forget. But please do join us again next week, where we have Dr. Arik Kushenbaum talking about Are We Alone in the Universe? But finally, let us all once again say a very special thank you to Professor Philip Jones. Thank you.